what I want to do today is to talk a little bit about the history of local area networks, at least from the standards perspective. And what I want to begin with here, at least my recollection of the state of communications in the mid-1970s. And we go back roughly 40 years, and we're going to cover about a 10-year period. Talk a little bit about some of the early standards efforts in trying to get the computers to talk to each other. And I'll get into the IEEE standards setting process and the evolution of local area network standards as they came out of there. Specifically, we'll end up with Ethernet and Wi-Fi as the kind of standards that came out of the 802 process. Since we're in a computer history kind of a place here, what was the world like 40 years ago? It was pretty primitive. No cell phones, no internet, no Facebook. People wrote letters actually by hand and put them in mail and mail them to each other. It was, you know, how did we do it? And this is roughly what it was all about. We sat around in caves and grunted at each other and talked about the last mammoth hunt.
About 40 years ago?
About 40 years ago, yes. Computer communication wasn't that much better, really, when you come down to it. The computers were standalone things, big boxes in glass enclosed rooms in corporate headquarters, and you could walk by and see the technicians inside mounting tapes and pushing buttons. And if you want a computer job done, you submitted your deck of punch cards. If you were lucky, maybe you had a terminal that ran at 1200 baud, maybe. So anyway, it was, computers were very insular, and they really didn't communicate with each other. The major force of the day was IBM, and it was IBM and the Seven Dwarfs. So can anyone name one of the Seven Dwarfs?
Burroughs.
Burroughs, yes, good. Any other dwarfs?
Unisys?
Yeah.
Honeywell?
Honeywell, right?
Control data.
Control data. Cray. Well, also, Cray is actually alive today yet, sort of. There was Data General, Standard Computer. Anyway, the idea was that the dwarfs all wanted to get in bed with IBM, but IBM had a pretty tight rein on how its computers worked and how they communicated with each other or with the peripherals. And the Department of Justice had to come down and, instead of breaking them up, because they were pretty monolithic at that time, they made them open up their specifications, and so we had some de facto standards. So this is basically stuff that already exists, and then people use those standards to make up interfaces so they can communicate with the computers. So yeah, the basic philosophy of those days was that you try to keep a tight rein on what you allow attached to your computers, sort of like Apple does today, in that they control everything, and then everybody else is frozen out. And if once you bought into somebody's system, then you were there for the rest of your working life at least. So that all changed in 1975, where we had the first Jura standard. That is a standard that was put together by people in some organization or other. This happened to be the IEEE, and the 488 standard came out. It was shepherded through by a guy named Don Lockery, and he was with Hewlett-Packard. And basically this interface was known as HPIB, Hewlett-Packard Interface Bus, or GPIB, the General Purpose Interface Bus. It was a byte wide of 1 byte, a megabyte per second. Before the standard, if you wanted to build a automated test system that contained programmable instruments, you got yourself a computer and you got different instruments that had interfaces to them, and then you proceeded to build custom interfaces for each one of these separate instruments. This took a lot of time, very expensive, difficult to document, difficult to replicate. What the 488 interface did was you bought a computer with a 488 interface on it, and you could talk to instruments that had that same interface on it. It was a huge success. It really opened up the world of building instrumentation systems. So the real benefit was, as the costs of building the computerized instrumentation systems went down, the sales went up exponentially. So a lot of people made a lot of money using this interface to pull things together. If you know National Instruments, that's where they got their start, with that interface. I was hired into Tektronix to look after Tektronix interests in this area, to go to the standards meetings for follow-on work to the 488 interface, and to bring it into Tektronix where Tektronix would build instrumentation in some uniform way that made sense to tie things together. Unfortunately, the 488 interface was rather limited. It really didn't address computer communications in general. And I was talking to somebody someday and said, well, you know, there's an outfit at Purdue University, and they've got a workshop for industrial process control. And one of their workshop topics is trying to tie together computers that run refineries. And so I went to the Purdue workshop and learned all about refineries. This is a really nice one here. You see there's nice white-capped mountains in the back and pure waters of the Puget Sound in the foreground. It's a bit of a misstatement. Those are really pretty nasty places. You have oil tankers coming in on one side, and it goes through, the oil goes through the various processes, and out the other end comes gasoline or heating oil or fuel, jet fuel or lubricants and things like that. And the places are really quite exacting in that computers run the whole thing, and the computers better be right. If some computer turns on a pump, but the valve on the other side is not open, then you get a pipeline that breaks, and then you have a fire, and then that nice background there disappears in a bunch of nasty smoke and plumes. And anyway, it's very exacting. Any kind of downtime is measured in hundreds of thousands of dollars per minute. So it's people want, when they put up a refinery, they want it to work well, they want it to work all the time, and these things run continuously pretty much until they're shut down for some repair or some refurbishment. So the Purdue workshop had a group of people that looked after the computer communications aspects of refinery operation. The workshop was run by a guy named Ted Williams, and one of the groups was to come up with a standard for a data highway for process control, or ProWay. This was in the early 70s. I joined up with them in about 76, and they were really pretty far along as far as modern data communications technology goes, seeing as how they came out of the area of process control, which wasn't really mainstream data communications or computer communications. What they wanted was a vendor-independent scheme. Otherwise, you had Honeywell and Foxborough and other people vying, say, why doesn't the whole industry use my kind of stuff? But you know that was never going to happen. So what we tried to do was come up with a basic requirements. What do you need for a local area network in local being, in this case, a refinery. And what they wanted to do was to have peer-to-peer passive media. What that means is that all the communications doesn't go through a central computer somewhere. Any computer can communicate with any other computer over some passive media, like a pair of cables or something of that nature. It had to be deterministic, because when you tell something in the refinery to do something, it better happen right away. If not, well, maybe yes and maybe no. And it had to be extremely reliable. So let me get into the technology a little bit, because it'll be background for what I talk about later. One was, I mentioned this ISO 7-layer model of communication. And you can think of that as two high-rise office buildings in, say, downtown New York. And at the top sits some CEO that wants to communicate with another CEO up here. Well, there has to be, they can't shout to each other directly. So what has to happen, the CEO scribbles a letter, passes it down to secretary, secretary types it, passes it down to the mailroom, passes it down. It finally gets down to the delivery boy that runs a bicycle on the streets, runs it over a road, and that message goes through the same kind of thing going up to the other office tower. That's roughly what this 7-layer model is. What really mattered for the people in the refinery was these 2 layers. Just the media, that is, what kind of cabling is going to be used, how the data is going to be sent, and what the data packets will look like. So that was the extent of the work, just the first 2 layers. As these folks at the Purdue workshop were talking, there was a standard that just had come out. It was called HDLC or SDLC. This is computer-to-computer communication. There was an international standard been passed. Unfortunately, this guy, Gerald Funk, showed up and showed that it doesn't work. That was kind of an embarrassment to everybody. And the reason it doesn't work is, it works like this. If you have a device that is transmitting data, and it goes over a wire, and you have a device that's picking up the data is sent as a packet. And the way that packet is delimited is by a flag in the front and a flag in the back, certain data pattern. And then in the middle is the actual data you want to transmit, and then a CRC is generated. It's a code that's based on the data that's been transmitted before that is transmitted along here. Now, the receiving device sees a flag and says, aha, the data is starting. It starts pulling in the data, and it's also generating the CRC. And then when it sees the end flag, and it says, okay, I've got this data packet. Let me see if I received the right kind of code to know that the data is correct. And this guy Funk, the Swiss, I don't know where he worked in Switzerland, but he showed that you could have single bit errors in this data and the CRC would not pick it up. Improbable, but possible. And for the guys that are doing process control, that's pretty important. If you tell some piece of equipment to turn on or to do something, and if you get bad data, you're going to have problems. So the idea was that whatever else ProWay did was they would come up with this scheme where you could have 4 data hits and still be able to have the CRC pick up that there's an error. And that was pretty important. So this is known as Hamming distance of 4. Hamming was some information guru that I can hardly spell the name of, but anyway, he came up with this concept. And so the requirement for the ProWay standard was there should be strong delimiters that you know for sure when the data is starting and you know for sure when the data is ending, and the CRC and data are such that you can detect up to 4 errors and still say this is bad, not passed along as good. Keep that in mind as we go through here. Graube was very forward-looking kind of an effort, but it was really quite specialized in that not everybody runs refineries, and not everybody's willing to pay the kind of money that refinery people are willing to pay to put up computer communications. Somewhere along the line, I ran into a guy named Robert Stewart, and he was a mover and shaker in the microprocessor standards arena. And so I was kind of lamenting that there is no standard for general computer communications. And so he says, well, why don't you start up an IEEE standards effort? And, I didn't know how to do that. And so he got the forms and helped me fill them out, and we sent in for a project authorization, and that was granted by the IEEE. And then I had to go in front of the American National Standards Institute. This is the organization that coordinates standards within the US, and it coordinates internationally. So this is to make sure that you don't have different groups popping up here and there that are coming up with standards for the same thing. Anyway, that was approved, and then it was basically approved. The charter was for a 1 to 20 megabit per second communication scheme up to about 4 kilometers in length. Somebody also penciled in there that we should also study metropolitan area networks up to 50 kilometers or so. And the basic idea was to provide compatibility between differently individually manufactured pieces of equipment so that they would work together without a great deal of programming or customization. So the idea was to come up with a single standard that could be used by the whole industry for computer-to-computer communication. So the first meeting was in San Francisco. There were 79 participants, and that was a bit of a interesting meeting. It'd be like us trying to get together here, trying to do something in common where nobody knows each other. And so we had to figure out, first of all, why are we here? What are we trying to do? And how are we going to go about doing this business? So it became an exercise in what I call electro-political engineering. So why are we here? Well, here's why we were there. I think everybody bought into this one pretty much without a lot of explanation. If there are these standard interfaces, then it's going to be a lot easier to interconnect computers. The sales are going to go up, and everybody's going to make money at it. Remember, this is 1980, so there weren't that many computers around yet, and personal computers were just starting to come into being in a little wider scope than just the hobby people. So, first thing we did was to lay down some function requirements, and that is try to come up with a standard so that we have the interoperability of different manufacturers. So the standards had to be definite enough. You couldn't just wave your hands and say, well, we're sort of going to send some data maybe this way. It had to be fairly specific so that people could design and build equipment to guarantee the interoperability. We wanted to have peer-to-peer, shared media, no central processor. And that central processor was probably kind of a dig at IBM. Nobody wanted to have a way to have to hook up computers when they had to go through a central computer, which in those days would have been an IBM. And we wanted to have reasonable quality data transmission, low bit error rates so that the method of sending data was reasonably secure, and Hamming distance of 4. So you all know what Hamming distance of 4 is by this time, right? So the way we organized initially was to break into 3 groups. One was going to look at how the packets were formatted, how they're going to be sent. There had to be another layer in here that the ISO 7-layer model didn't anticipate, and that is media access. If you have a shared media, then who gets to talk when? It's like a telephone party line way back then in the 50s kind of thing. And then the media itself, of course, the wiring and the way that you send signals down the wires. We also had to come up with operating rules, and that is people that came to meetings were there as individuals, not as company representatives, so there was no particular company orientation necessarily. IEEE membership was not required, and you had to attend 2 out of 3 meetings in order to vote. So we didn't want to have people coming in off the street and some issue would come up and somebody that was totally ignorant of what had gone before would get to vote on it. So the 2 out of 3 is what got us open. Yes, sir.
But the meetings were open to anybody?
Anybody, yeah. So there was a small fee, like $30 or something like that, to cover the cost of Xerox machines and things like that. And then as we got the standards more solidified, then we had to go through the IEEE rules, where it had to be 75% of the people that were qualified to vote would vote affirmatively, but those who voted negatively had to justify why they're voting negatively. I'm not saying I just don't like it. They had to say what would have to be changed in order to get the yes vote. And those would have to come back, and we'd have to go over that again and re-vote again to see if we pulled in enough negative votes to clear it. And after a while, basically say, okay, we've tried to accommodate everybody, but we're not going to get unanimous votes. So that was the mechanics of the operation. And the work started pretty curiously here. We have meetings initially 4 times a year. And that was of the main group, all of 802. The individual interest groups would work on their own, and even smaller groups would work on their own. So there was a huge amount of work that was going on here. And this went on for about 2 years. And we finally came up with a draft C of what all these people had done, all the different groups. And I basically said, look, we've been at this for a while now. We got to show some results to the outside world. There was a lot of interest in local area networks at the time, so we had to show something. The interesting thing here is to get the data for these groups. The individual group chairman submitted mag tapes. Of course, they were in all kinds of funny formats, so there was a huge problem with trying to even compile the data into something that was readable. In one case, I had to have my secretary retype the whole section because it wasn't decipherable in any way. So at that time, I called up Microsoft and I said, I want to talk to Bill Gates. Of course, they wouldn't let me talk to Bill Gates, but they asked me, what do you want? I said, well, I want 12 copies of Word. And they provided the 12 copies, and so now we had a way to communicate because everything was in Word format thereafter. So that was a good move. Without standards, you really can't communicate. This draft C was really a kind of a statement of the fact that the committee had failed. This is a compilation of all the different techniques you can use for sending different kinds of signals over different kinds of wires and different kinds of data patterns and this and that. And that does not make a standard. So we basically had to say we can't go on like this. We really need to come down into individual groups that work on a specific technique. At that time, there was a lot of contention between the people that wanted Ethernet-like network, between the people that wanted the IBM-type network, and people that wanted a process control-type network. So instead of trying to come up with one standard to cover everybody, we broke up into these individual groups here. And then there was an executive committee to make sure that things stayed coherent, that new groups did not proliferate, so that we'd have thousands and thousands of standards each one based on some individual's favorite technology. So what I will do is go through some of these things and show you how things evolve. Okay, the basic crux in local area networking is the need for shared media. If you have 5 computers that are trying to communicate with each other, and if they had point-to-point interfaces, you can see there's an awful lot of wire there. If you come up to about 10 or 20 or 50 or so computers, then you know it's just going to be a total mess here. That's not workable. So if you're going to have a shared media, then you have to have some way to get onto that media to share it. Now one of the ways is to use something called a token bus. This is what the process control guys wanted. So you have a single cable here, and along the cable there are taps. And the taps are such that any one of the stations down here, computers trying to communicate, can fail. It won't affect the media itself. The rest of the devices can communicate. The way this works is that there's a token message passed from device to device. So if device number 1 has a token, it can send out a message. So the message will say, okay, device number 4, I want to tell you something. So this message will go over, everyone will hear it, device number 4 will pick it up, and it'll have that message. If station 1 doesn't have anything more to say, it'll send a token to station number 2. And now station number 2 can decide whether it wants to send something out or not. And so that token gets passed from station to station. It works, it's deterministic, but it's horribly complicated. How does this thing get started to begin with? Who gets this token to start with? What happens if you want to add station number 6? What happens if station number 3 drops off the line? So you have to have all this taken care of, and the standard, the 802.4 standard, is written in Pascal. I can't read it, I don't know what it does. I mean, I have an idea, but it's horribly complicated. There was a chip, Motorola made a chip for this, and it is being used still. It was initially being used by quite a few process companies, Foxborough, Honeywell, Hitachi, AEG. Anyway, it got a fair amount of play in a very narrow market segment. Okay, there's an easier way, and that was the IBM way. Bob Donnan was an IBM guy that they pulled out of retirement. He was a wise old fellow who could get his troops together from the various divisions, and so they wanted to do a token ring. They'd been doing a token ring in some laboratory in Zurich, and the idea there is that the devices are all connected up into a ring, and so in a sense, the one device has a token, it sends the token around. When it receives a token, the message back, token or message, then it passes the token on to somebody else. And so the whole idea of who is has a token, how do you add another station, it's a lot simpler, and it's a very much more elegant kind of a system. And the way it's really implemented is that the devices don't send messages to each other directly, but they communicate with the central hub. And the hub does nothing more than monitor the data as it's passing through. If one station drops off the line, is not responsive, then the hub cuts it off, and the token or the messages continue through the rest of the system. And that's really a lot more practical in a sense, because that's the way offices are wired. There's a wiring closet somewhere, and the twisted pair wires, which is what IBM was proposing here, that's the way you wire to the wiring closet, just like you with your telephone twisted pair wiring. That patent came out, and somebody built a semiconductor part for it. The problem is, there was this guy named Soderblom, And Soderblom was a consultant IBM had in Sweden. And back in the early 80s, IBM had put together some sort of a system in Sweden. And Soderblom was a consultant. And Soderblom looked at what IBM was doing, and he went out and got himself a patent on it. And then he said, IBM, you can't sell this stuff into Sweden because I have a patent. And so IBM paid this guy $5 million, stole. And back at early 80s, that was a fair chunk of money. But IBM got exclusive rights on this thing. And so they were home free. But now we in the IEEE 802 committee come up with the 802.5 standard, and suddenly Soderblom shows up. And so he wanted a fair amount of money for licenses for the equipment that used this technology. And that sort of disintegrated. It really wasn't very much in the way of token rings. It was very, yes sir?
Doesn't this also have the problem that you have a central processor essentially? And
No, it's not really a processor. It's just a switching.
but it's a single point of failure.
Yes, it is. Yes, it is.
So it's a switch. You know, so then it's.
And it's not peer-to-peer, is it, really?
Yeah, it is peer-to-peer. The hub doesn't have any intelligence. I mean, it's stupid. It just passes stuff. Anyway, that's the way it was. So I can't turn back the clock, and you should have come to these meetings and straighten people out. The third technique is something called CSMACD. Remember that set of letters, and you can impress people at cocktail parties. And basically, what this scheme does is you have a cable where you have devices attached to it, and any device can talk at any time that nobody else is talking. And that works pretty well. If we're in this room here, and you guys want to have a conversation, talk to somebody else, you can, if I'm not talking, you can speak up and things go on. Once in a while it could happen that two devices will try talking at the same time. And that they both recognize that there's somebody else trying to talk, and they're polite. They stop talking for a random amount of time, and then they'll try again. If they have a collision again, they say, oh, there's a lot more people wanting to talk. I think I'll stop for a longer amount of time, but longer amount of time, random but longer. And so eventually what happens is that the congestion will clear out. Anybody can talk to anybody else. It's a very elegant scheme. There's some limitations to it, like 100 meters for the main cable, because that's the amount of how the listening is done. If you listen for a certain amount of time. And at any rate, it was invented by a guy named Bob Metcalf. And he went to work for Xerox PARC, and somewhere along the line, Xerox and Intel and DEC got together, and they said, we want to make this a standard. And this was going on at the same time that we were trying to formulate a standard within the IEEE 802. They came up with their blue book here, which defines what this network is all about. It's very well written, it's very concise, it's very detailed, it's beautiful. So with Intel in there, they were also making a chip for this. So a standard with a chip, without a chip, is almost useless. So there's a lot of things going for the Ethernet scheme versus what was being formulated in the IEEE. Now, we weren't that far off. I mean, there were Ethernet champions within the 802 committee as well. The trouble is that Ethernet, as defined by the Blue Book, the data format was something like this. There was a preamble, a series of ones and zeros that were being sent, and then there was a destination address, source address, data, and a frame check sequence, and then the transmission just ended when there was no more signals. Now that's all well and good, but if you have a single bit hit here, you don't know where the data starts. So the frame check sequence, however good that might be, doesn't give you any protection whatsoever. So if you don't care about the quality of your data, this will sort of work, but this does not have the hamming distance of 4. And that's what we had to have as far as the 802 functional requirements went. The way we fixed it in 802 was to put a length field in here that said, okay, this is how long the data is supposed to be, and that way we will know that the frame check sequence is going to be correct. Now it still doesn't give you a hamming distance of 4, but the really smart guys in the group figured out that the times that you would have errors are so vanishingly small that it really doesn't make any difference. So for all practical purposes, there is a hamming distance of 4. So that's what's in the 802.3 specification. So that's why it was, as far as IEEE went, that's why we didn't pick up on the DEC, Xerox, and Intel scheme, which was very nice, but it had this fatal flaw. Now after the 802.4 Ethernet spec came out, that initially was for the big fat yellow cable. It was about a ½ inch in diameter yellow cable. It was stretched through a building in the ceiling or something like that. And to get to make an attachment to it, you have to go up there with a special little drill bit and drill out the cable. And then you had to attach a vampire tab and do it in such a way that you didn't short out the cable while you're doing this. And well, that's just not the way offices are wired. I mean, every time there's an office move or something, somebody's going to crawl in the ceiling and be drilling cables. That's not quite right. So the next in the series of the 802 standards, there was a small coaxial cable that was proposed, and that was proposed by guys at an outfit called AMP, the connector company in Pennsylvania. They were a big-time company at that time. Anyway, what they wanted to do was to run a small cable into wall outlets and on again. And if nothing is plugged into the wall outlet, the cable simply goes straight through. If somebody plugs in one of these special AMP plugs in here, then the cable gets passed to the computer and then back out again. So it still maintains the Ethernet characteristics without having to deal with the fat yellow cable. And next in the evolution was that somebody, I've got to look up this guy somehow, but there was a company called Synoptics in the Bay Area, and they figured out they could put Ethernet signals on telephone twisted pair wires, and they would run them through a hub. And that's really the way offices are wired. Twisted pair cables and to a central point. So it used the telephone wiring, telephone jacks that we're all familiar with, the RJ4046, I guess. And the rest is history. This is, if you're going to have wired Ethernet, that's the way it's used today. That itself has evolved in that the hub evolved to a router, to where you could have hubs that are tied together in a hierarchy, to where signals could be, connections could be made with computers between the hubs, and then you came up with switches, which would take in the data and figure out where it's supposed to go and send it on. So the whole thing of CSMA CD went away. You don't need that anymore. When a device needs to transmit, it simply transmits. It goes to the switch, and the switch takes over from there, and that's all the rest. So we've gotten away from the peer-to-peer communication that's strictly on a passive kind of media, but this is the way the real world works. So then, of course, there was other additions where you can send power over the Ethernet cable now, and an Ethernet cable you can go to 10 megabits per second, 100 megabits per second, gigabit per second, and I don't know where it's landed up. 40 right now, yeah. So anyway, it's crazy stuff, but it's all over, you know, not telephone grade twisted pair wires, but good quality twisted pair, and it works. And then a kind of a funny thing happened. We had a guy named Vic Hayes come into 802 meeting, come to the executive committee and say, look, I want to start yet another group, and I want to do Ethernet over radio link. Well, that wasn't quite in our charter, you know. That wasn't what the IEEE charters were, or what the ANSI agreed to. But we thought, well, guy's harmless. I mean, what is he going to do? I mean, this has never been done before. And so Vic, he was from NCR, from Holland, and he came out and he had his people group, I don't know, about a dozen people. I'd sit in on his meetings and I didn't understand a word he said. I mean, it was all this modulation and phase coding and this and that and the other thing. And then about 3-4 years later, we started seeing Wi-Fi. And it's all over the place now, so it just came out of the blue. So that's kind of the evolution of the 802 standards. There were other groups that are involved with broadband cable, people involved with fiber optics, people involved with this and that. None of those really reached the standard stage, and the standards that did come out, I think the only really worthwhile ones were the Ethernet one, the CSMA/ACB one, and its evolution, and then Wi-Fi. Well, we all call it Ethernet. The original Ethernet is long gone. It's the smile left on the cat's face in Alice in Wonderland, where the cat is faded out, but the smile of Ethernet is... There was another group that dealt with the logical link control, that had to do with the packet format and how things are related to the higher levels of protocol, and how it all fits into the international way of naming things and doing things. There was a lot of discussion about connection-less versus connection-oriented communications, which I won't get into. If you're interested, the IEEE Spectrum magazine had a very good write-up, I think last December issue, talking about the evolution of the international standards effort in these protocols and how everything is switched over to the TCP/IP. If you are really interested in this kind of stuff, there's a little book out on the standardization of local area networks that talks about the early days of the standardization, and it looks at it more from the business perspective as to who was doing what to whom and who was going to make money at this stuff. It's interesting reading in a sense, but it's back in the early 1980s kind of thing. The IEEE has a computer society group that's looking at the history of computing, and they have a website there you can go and look at if you're interested to look at this stuff. And they have interviews with some of the movers and shakers of the day of what how the local area networking evolved. So what I try to do is to just give you some idea where we came from, what the early standards were like, and how things evolved over time. I turned over the chairmanship of the 802 committee to Don Lockreed at the end of 10 years, and he ran it from there on. When I left, we had over 300 people in the committee. I came back for the 20-year anniversary meeting, and they had 1,500. And they said, well, if they keep going like that, you know, we're going to take over a small city here in the United States to run these committee meetings. So that's really is what my talk was all about. If you have any questions, I'll be glad.
That's CDMA. Is that the same as the cell phones use?
CS.
CS.
That's CDM.
CDM.
The carrier sends multiple type of things, and that's what you do.
Okay.
Yes.
I'm sorry, I missed the first couple of minutes, and maybe you mentioned this already, but did Data Point try to push its ArcNet in data too in any way?
There was a little, yeah, there was some talk about that, but it really didn't go anywhere.
One job I had very early in the computer industry was pulling ArcNet out and replacing it with Ethernet.
There's a lot of stuff pulled, right?
Yeah.
I got it.
Yes, sir.
So the book that you mentioned probably would cover this question. Hopefully it's small enough in scope that you can answer it and not disappoint me there. But so Bob Metcalf is, you know, the big name, you know, in I guess the public's mind. It's the computer public's mind. On Ethernet, he's Mr. Ethernet.
Yeah.
How can you tell us how he materially benefited? I guess he didn't have a patent on that.
Yeah.
Translated into this, or
Yeah, well, he
blocking?
didn't. The patent is in his name that was owned by Xerox. And Xerox licensed the patent to anybody for $1 for, I don't know, for company or for individual station. Anyway, it's minimal. So it's recognition for Xerox. And the nice thing too is that Xerox had set up the addressing for Ethernet with 6-byte source and destination addresses, which is a huge, huge address space, and that is parceled out uniquely to the licensees. So if you get a license for Ethernet kind of system, you get a block of addresses, you administer them, and you make sure there's no duplicates. And that's really important in keeping track of what device is which. But, and then Bob went on to found his own company called 3Com, and I think he did quite well with that.
But
Yes?
Yes, talk about the upper layers like TCP/IP. Hitzler was saying that Xerox gave hints as how to do that based on AlphaNet. Is that true?
I don't really know. There was a lot of work going on. The International Standards Organization had quite an effort going on in defining these upper layer protocols. So they're not only for the communication, but for things like file transfer and sessions and things like that. And it was quite complicated. And what happened was that the Department of Defense, I think it was Berkeley Unix incorporated TCP/IP and made it virtually free, and so it just spread like wildfire. I don't know that much about it, but the TCP/IP didn't have enough address space, whereas the international effort would have. But as you know now that there is a new TCP/IP which is trying to correct some of these problems. Anybody else? Yes, sir.
Yeah, did the breakup into the subgroups get the inter-company battles down enough that allowed the subgroups to make good progress, or was that still a big issue on companies trying to posture to advantage themselves and the standards?
Well, their initial effort trying to come up with one standard was not going anywhere. It was just a compendium of different schemes, and nobody could build anything that was worthwhile. So I thought, you know, let's break up into these groups. Let's separate out the warring parties and let each one run at their own pace. And whoever comes out first and wins, fine. At least we'll have a small set of standards rather than no standard at all.
You started out with the process control industry and their high reliability. Did they end up getting, I don't know anything about process control, did they end up really using this as
Yes.
a reliable enough system for that?
Yeah, it's still being used. Honeywell is still, I mean, the thing is, there really wasn't the interoperability between companies. You couldn't take a Honeywell computer and marry it to a Foxborough computer, marry it to a Siemens computer. That it just covered the first two layers. But there was enough interest there to where there was a semiconductor chip, and people could now start building things on top of that.
So refineries
Yeah.
use Ethernet as a controlling
Well,
802.3.
yes and no.
Okay. That's what I'm
The
trying
part of
to-
a refinery that's really time critical do not use Ethernet. But once you get away from the individual operation of individual units within a refinery, then you have to have things like asset management, you have to have historians, you have to have ways to manage how much stuff you're going to be pumping through and what sort of stuff you're going to get out. And that's all Ethernet based. So the real-time control is not Ethernet, but everything else is.
Okay.